All right, ladies and gentlemen, welcome back to some more AP Chemistry with Mr. Kenton. As I'm slowly but surely working my way through Unit 1, we're at topic 1.3, which focuses in on elemental composition of pure substances. And so, again, you've got the textbook pages that this corresponds to, as well as the Brown and LeMay textbook questions that we did in class already. So, without further ado, let's move forward and continue our review of Unit 1. So remember in Unit 1, we looked at and we talked a lot about the differences between empirical and molecular formulas, right? And so remember, an empirical formula is simply the lowest whole number ratio of the atoms present in a molecule. So I'll go ahead and write that in for you guys. So formula with the lowest whole number ratio of atoms, right? And so this is going to be most useful for us as chemists when we're trying to look at percent composition, right? So this doesn't necessarily tell you exactly how many atoms of each element you have in the compound, but it does give you those percentages, which are going to be the same regardless of how much of that substance that you specifically have, right? Next, you have your molecular formula. Now, your molecular formula is going to be different from your empirical formula because it's going to tell you exactly how many atoms of each element are present in your compound. So it won't necessarily be the lowest whole number ratio. So let's just kind of write that. So your molecular formula tells exactly how many of each atom are present, right? And your molecular formula is always going to be some whole number multiple of that empirical formula, right? So your empirical formula, lowest whole number ratio, that molecular formula is going to be some sort of multiple. So you should be able to reduce a molecular formula or simplify it to get to an empirical formula, which is generally pretty straightforward and easy for us to do, right? Now, we've also got these terms. You've got atoms, ions, molecules, and formula units, right? And they each have their own unique place, right? So remember, we talk about particles. At the particle level, we would say something is an atom if it's just an element from the periodic table, specifically if it's a monatomic element, right? So something like calcium, for example, we would say that that's made up of atoms, right? Now, if I talk about an ion, that's something like calcium 2+, right? We would say that that's made up, just right now, that we would say that that's made up of ions, right? If something's a molecule, that'd be something like water. And then lastly, if we're dealing with something that's a formula unit, that's going to be something like NaCl, right? That's going to be a formula unit. Okay. Now, as we've seen, what is the difference between an empirical formula and a molecular formula? Well, like we said, molecular formula tells you exactly how many of each atom are present. Empirical formula does not. It gives you the lowest whole number ratio. And so I want us to think about, for example, if we think about benzene, it's an organic compound. Its molecular formula is C6H6. That's its molecular formula. But its empirical formula is not C6H6. Its empirical formula is just simply CH. And that's going to be equal to its empirical formula, right? And so, again, they tell us something unique, but the molecular formula tells us exactly how many atoms of each element we have. Empirical formula tells us the ratio of those atoms. And then just for thought, think about when do we use the terms atoms, ions, molecules, or formula units in terms of when we're writing out calculations and when we're talking about substances at the particle level. Think about when we would have to use those particular terms, right? And think about the examples that we just walked through above, right? Now, empirical formula and all of that we looked at on the previous slide lends very nicely for us looking at percent composition. This is a very common type of calculation that we would have to do, right? So to determine the percent composition of an element within a compound, it's like it sounds like we would take the number of atoms that we have of that element, right? We would multiply it by that atomic weight of that particular element. So we just look at the periodic table. And then we're going to divide it by the formula weight of the overall compound, right? Now, when you do that, you should get a decimal number, and then you multiply it by 100, and that's going to tell you your percent composition of that particular substance, right? And again, just to clarify, AW there stands for the atomic weight of the atom from the periodic table, and FW is going to stand for the formula weight of the compound. Now, might help us if we take a look at an example. Let's see if I can make this work. I'm getting all kind of fancy over here. So let's say that you wanted to figure out the percent of oxygen in water. So let's say we want percent oxygen in water, right? So in water, there are 2 oxygen atoms, and each oxygen atom has an atomic weight of 16.00, right? And then our formula weight of water, H2O, is going to be 18.02, right? So you've got 18.02 is the formula weight of water, right? So you got, oh, Mr. Kenton made a huge boo-boo. It's not supposed to be 2. There's only 1 oxygen, right? Ignore that. It's a 1, right? I was thinking of hydrogen. There's 1 oxygen, and there's 2 hydrogens. So you got 16 divided by 18.02. You get, that's going to be equal to 0.888. You multiply that by 100, and you get that water is 88.8% oxygen by mass, right? Pretty straightforward calculation. Now, here's an example problem. We're not actually going to walk through this one, but think about what information can be found based on what's given. Freons are gaseous compounds used in refrigeration. A particular freon contains 9.93% carbon, 58.6% chlorine, and 31.4% fluorine by mass. So the question becomes, what can be found with this information? Well, because they've given us the percentages of carbon, chlorine, and fluorine, we should be able to figure out what the empirical formula of this particular compound is. Okay, we're not going to walk through how we would do that in this particular video. Maybe I can do another one later, but using that information, we could figure out what the empirical formula is for that particular substance, right? Now again, how is the empirical formula of a substance and an element percent composition by mass related? Well, knowing the percent composition by mass and the empirical formula, you should be able to use those percent compositions by mass to actually help you solve for the empirical formula like we saw in the previous slide. Now again, just real quickly, when we talk about particle representations of what those looks like, so if you were asked, for example, to draw what a molecule looks like, remember it's going to look a little bit different than our ionic compounds. Your molecules, those are your covalent compounds, your nonmetals that are bonded to nonmetals. Your molecule would look something like, I don't know, I'm just thinking of water again. You'd have your hydrogen attached to oxygen, attached to hydrogen. Got your lone pairs on your oxygens. Whereas your formula unit is going to look a little bit different, right? Your formula unit, you're going to have kind of your nice defined crystal lattice structure where you've got your small metal cations and your larger non-metal anions. Not doing a pretty good job of keeping them consistently the same size, but you know, you kind of start to see this pattern that it follows, right? And so that would be the representation of your solid. Now you could think of the formula unit. Also, you could think of it as Na plus that's interacting with Cl minus. And the fact that they're close together, that would represent one formula unit of sodium chloride, right? Now, the last thing I want us to look at in this particular topic is the law of definite proportions. So specific substances always contain elements in the same ratio by mass. So for example, and that makes sense to us, right? Like water is always going to have the same ratio by mass every single time. The mass ratio in water is always going to be, for every 8 grams of oxygen, there's 1 gram of hydrogen, H2O, right? And hydrogen peroxide, that ratio is going to be a lot different, right? So when you look at that, you've got for every, like if you look at the total mass with that 32, 34, so when you break it down, it should be something to the effect of for every, 16 grams of oxygen, there's going to be 1 gram of hydrogen, right? Now, for number 2, if 3 grams of element C combine with 8 grams of element D to form compound CD, it's asking how many grams of D are needed to form compound CD2. I'll leave that one for you guys to figure out. But for the third one, if 2 grams of element A combine with 10 grams of element B, then 12 grams of A will combine with, you should get 60 grams of element D, right? And that's just to match up with this law of definite proportions that states that substances always contain elements in the same ratio by mass. Now, if we're looking at this particular data table, and let's say we were asked to figure out what would we need to identify if the law of definite proportions is being shown in this particular compound, what pieces of data would we need? Well, I hope that you would say, well, Mr. Kenton, I'm going to need the data that's in the mass of P and the data that's in the mass of oxygen. Those are the 2 data pieces that we're going to need. You don't necessarily need the grams of phosphorus to the grams of oxygen, because if you're given the first 2 data points, you could figure out grams of P versus grams of O. Right? Now here, just some questions for you guys to consider. They give you the masses of P and O respectively, and what information, what statements can we make about what's true of compound A and compound B, and what's true of compound A and compound C. Right? Now, take a look at that. Use that claim, evidence, reasoning, and rebuttal to help you kind of come up with your answers. But we should be done with that particular topic. So thank you guys for stopping by. Hope this was helpful. And if you have any questions, you know where to find me.